This is a YouTube channel dedicated entirely to coughing. Over 500 videos and counting. Some are 30 seconds, some are a few minutes, some are over 10 minutes. But that's not the strange part. There are scripted 6 scenarios, there are commissioned cough recordings, there are limited cough releases. People submit coughs, some get featured, some get sold. There is somehow a functioning cough economy. Now, most people would see this and think, yeah, that's weird, but I've seen worse, and keep on doom scrolling. But not me. My brain is a bit broken. While everyone else is using AI to automate their jobs, I was looking at this weird, localized internet anomaly and realized something funny. This is structured, this is consistent, this is hours upon hours of perfectly labeled machine learning training data. So I asked myself the best question of my career. Is this enough data to train an AI to cough? Could I completely automate this guy's weird little internet hustle and replace this entire ecosystem with mathematics and science? To answer those questions, we need to start off by gathering and cleaning all the coughs. Now, downloading 500 videos from a single channel requires scraping, which strictly violates YouTube's terms of service. As a proud YouTube partner and an upstanding citizen, I would never do that. Never. But coincidentally, I checked the nest of my geese and found some eggs and a mystery hard drive. I plugged it in and wowzers! It's stuffed with gigabytes of raw, uncompressed .webm files of girls coughing. Wow. What a coincidence. Thank you, Goosies. I love you. But to make it easier to process, I had to turn them into .wav audio files. So I made a Python script just to do that. It turned all of the .webm videos into .wav files I can actually use. Okay, so let's have a listen.
That tastes like heaven.
You can see that there's a problem with some of this audio, or most of them actually, is that there is speech and like background noises. We can't train an AI specifically on this data. We need to isolate the coughs. We only need the coughs. There should be no yapping. It should just be one singular cough. What we're gonna do is one file is just gonna be one cough. So let's fix this. I wrote a segmentation script using RMS thresholding. Basically, it scans the audio for whenever the volume suddenly spikes. It would listen to the background noise of each specific video. It figures out the baseline, room tone, doubles it and says, okay, anything that's above this line is a cough. This lets me isolate and identify the big ass spikes, which usually tends to be coughs. On top of that, I also programmed in some filters. Basically, high-pitched sounds like talking gets thrown out. Anything that isn't a violent burst of noise gets thrown out. Sounds that are too musical also get thrown out. So with RMS thresholding and these filters, we should be able to select and find the coughs, and then after that we're just gonna have like these filters to figure out if they're actually coughs. So if there's like singing, talking, I don't know, fucking background music or something, it should just be not selected and it should be excluded. So after running the scripts, this is what I got. Pick a random one here. Oh, that's pretty good. Ooh. Ooh. Ooh, that's good. It's beautiful. Needless to say, I'm really happy with the results. But I was also gathering some stats. I found 481 videos. The raw duration is 8,313 seconds, 32,248 segments. So the total duration of all the coughs is 500 seconds. The average cough per video is 59.6. And the maximum amount of coughs in a video is 271. So after the filters, we're now left with 26,000 coughs, which is it's pretty good data. It's quite a lot. So now one file is one cough, which is perfect. But we need to convert it one more time just for the machine to actually learn from it. The raw audio we have is basically a list of 44,000 numbers per second. It's too dense, it's too noisy, and it's too much for my little GPU. So I converted every cough into a Mel spectrogram, which is just a picture of sound. The horizontal axis is time, the vertical axis is frequency, and the brightness of each pixel is just how loud that frequency is at that moment. The model can look at these images and just learn what a cough looks like, which is easier than learning from raw waveforms. And with that, I finally have it. A mathematically PSA 10 dataset. Now we can actually go train the AI and build a brain. So the modern solution, well, at least in 2026 that I know of, is diffusion models. How diffusion models work is that it's gonna create like a random image like this. It's pretty much just noise, and then it's slowly going to step by step reconstruct an image just from the noise. But instead of this funny looking pigeon here, it's going to create our little Mel spectrogram that I talked about earlier. But here comes the problem. This type of diffusion models are quite hard to train. For example, this fast time and condition latent audio diffusion. They use 64 A100 GPUs. A singular A100 GPU is like 12 to 13 times faster than my current shitty 3060, and 64 of them. Another one is Audio X. They used H800 GPUs, which is about 36 times faster than my GPU, and it has 4K total GPU hours in total. Let's just do some quick math. 24, 6,000. Wait, is this real? 600,000 days divided by 365. 16 years. Bro, my 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 GPU is not gonna do it. So that is sort of the problem. Thank you for my Patreons, but that is not enough compute power for this. Using the H800 example, 4K GPU hours is probably maybe 10, maybe 8 to 15K in total US dollars. So what we're gonna be doing is, instead of a diffusion model, which is the proper way to do it in 2026 at least, the meta that I know of, we're gonna be doing something a bit more simpler. Now, I do know my dataset is definitely smaller than these examples, and a diffusion model will definitely work. But honestly, this is like a coughing baby versus hydrogen bomb situation. Like, I don't think I need it. I don't think I need that much power for this. Like, I don't care if it's shit, to be honest. So the question now is, how am I gonna train an AI that's cheaper than diffusion models? The answer is, funny enough, is already in how stable diffusion and other diffusion models already work, which is a variational autoencoder. So what this entire algorithm does is that it takes this image and it tries its best to recreate this. Afterwards, we're gonna completely remove the input and encoders, and we're just gonna make up our own numbers pretty much in the latent space. The AI would pretty much create its own original cough, which is pretty much what we want. So with the game plan out of the way, let's get to training. So for this training run, we actually was left with 16.3 thousand coughs. I know it's a bit less than what I said earlier, which is, I think it's like 26,000, is it? Or 32,000. Basically, I was pretty much just playing around with the filters a bit more to make it a bit better. But the real final training data set is 16,000, which is what we have here. So it was trained for 300 epochs, and the entire run took about 3 hours on my 3060. Just saying, right? This would have been done in like 10-15 minutes on a pretty powerful GPU, which is like, it's pretty crazy to think about how slow my 3060 actually is, despite like being able to play games and whatever pretty decently. So after 3 hours of training, this is what our VAE is able to do now. So this is the original image, and if you look over here, this is the reconstructed image. As you can see, it's trying. It's definitely trying. You know, there's the purple here, then like this bright spot, like this bright spot. You can see that even this bright spot, like it's definitely trying its best, but there's probably a lot of reasons why it's not as good, and like I can't be bothered to figure it out. But for our case at least, this is actually good enough. So this is the original cough, and this is the reconstructed cough. But you can see that it is trying, it is close, it is getting close. Alright, so now that we know the quality of the reconstruction, how would it actually look if we remove the input image, the encoder, and just make up a bunch of random numbers? Basically now, we're gonna tell it to make an original cough. And yeah, so I have mapped it out. And looking at the MEL spectrograms, it's looking kind of dire. Let's have a listen to how they sound like. Sample 0. Sample 1. Sample 2. And sample 7. Now, this might still look rough, but that's fine. I'm gonna tell you why this is fine at the moment. You can sort of hear that it is resembling a cough. Like if you use your imagination, if you use your big brain enough, uh you, you could say that this is a cough. If you just imagine like the missing details, like use your brain and imagine the missing details. This is a cough, and we can improve on this and we can work on this. But I am really happy with what we have so far. Basically, we can literally create this cough infinitely, or pretty much a lot of times. But we need to do some steps to make it a bit better, and we're gonna start off with the first one. So this is actually the latent space. This is pretty much all the coughs graphed out. I guess you can sort of say that this is the brain of the AI, and this is every single knowledge, every single thing that the AI knows about coughs. Now, the problem with how we were doing it is pretty much what we were doing. Boop, beep, boop, beep, boop, beep, boop, beep, boop, beep, boop. Yeah, basically, some of them are landing in, let's just call it no man's land. If we give the AI this number, like the AI doesn't know a cough near this area, so like what is it gonna do? So it's still gonna try its best to make something, but it won't be that good. So basically what we want to do now is to teach the AI where to sample from. So how we're gonna do that is with Gaussian mixture models. So instead of like selecting randomly and having this like this ones where like they're literally in the middle of nowhere, instead of having that, we're just gonna have it so our algorithm is just going to select data from here. So that, yeah, pretty much that's the idea. So this algorithm took actually like about 5 minutes to train. It was pretty quick. You can see that with GMM clustering, our spectrograms look way better and way healthier than what they were over here. Like, what is this? Compare that to this. That is a better structure than, whatever this thing is like over here. What are you? What is this? What are those? What are you? But yep, GMM clustering does work. That is way better. That's way better. So to summarize where we are at, this combo is pretty much 80% of the way there, but we just need the last few percent. And this last few percent is actually the most computational expensive, as well as the most important part, because like, well, it's a part that makes it sound good. Now, to make it good, we actually sort of need to understand what vocoders are. Basically, they're the algorithm that turns the little pictures that we have, the MEL spectrograms, into audio that we can hear. The one that I'm currently using is actually Griffin Lim. Peter Griffin. The reason why I'm using this at the moment is because it's just fast. It's very good for development and it's quick. But the problem is this: it's the quality is kind of bad, and like you can literally look over here from the page. This is literally made in 1984. So it's not good. So what we sort of want to do is we want to change the vocoder into something else, something better. We're gonna rip that out and use something a bit more it's still a bit old, but it's definitely a bit more modern. I'm gonna be using Hi-Fi GAN, adversarial network for efficient and high fidelity speech synthesis. Here is a quick comparison between Griffin Lim and base Hi-Fi GAN. Sample 0 Griffin Lim. Sample 0 Hi-Fi GAN. Now, you can see that Griffin Lim, Hi-Fi GAN is just way better than Griffin Lim. But there is still a problem, as you can see. The thing is, Hi-Fi GAN is not made to generate coughs. It's actually to generate speech, to talking. It's trained on speech and talking. This is not made for coughing. It's made for talking. So what we're gonna be doing is fine-tuning it. Basically, that means that we're just basically gonna teach Hi-Fi GAN on how to cough pretty much. So let's get to fine-tuning. We are training. We're going at like maybe 1 step per second or something shit like that. Look at that. We're training and that's a real GPU. That's him. That's the guy. That's him. He's training the coughs. Like right now. It's funny because like my SSD is running hotter than the fucking GPU, but we can fix that. Oh, you need to breathe, little one. Breathe. Breathe. Now let's see the new temperature. 68. Ah, 61. Now that is good. That is good. So we're just gonna sit on this, I guess. So here are some stats from our little training run. We went from 2.5 mil steps to 2.7 mil steps. Some interesting things that I started out on my local 3060 for 100 steps. This actually took like 30 plus hours. Oh fuck, I can spell. 30 plus horse. It's quite a lot of time, and I couldn't use my PC for that time. It was not fun. But thankfully I have like spare credits from this one website. I went ahead and rented an A40, which it only took 12 hours. It's like an A40 is not even that good, bro. So overall it took me maybe 42 hours, or maybe maybe 45, just because of like moving data around and processing stuff. So it took 4 or 5 hours on training it. As you can see, there is a sussy little drop here. When I went from the 3060 to the A40, I did a little oopsie. The nerd explanation is I changed the val data set. So it fucking dropped super hard. But here's the thing, right? The lower the better. So it's surely good when it just suddenly dropped. So it's surely good. Surely a good thing. Surely. So our Hi-Fi GAN with 2k steps. This is how it sounds compared to the base Hi-Fi GAN. Sample 0, base Hi-Fi GAN. Sample 0, Hi-Fi GAN 200 steps. Sample 1, Hi-Fi GAN base. Sample 1, Hi-Fi GAN 200k. I honestly think this is better. It's 45 hours worth of training time and maybe $5 or $10. Let's just say $5 to $10 worth of compute. Like, just a comparison, this is how the original Griffin Lim sounded like. Hi-Fi GAN, or Hi-Fi GAN. So that is it. That's the entire thing for Hi-Fi GAN. We literally just made it sound so much better. I think we are pretty much done. We can go make an unlimited amount of coughs that we want to. With the algorithm done, I made a website. Now, I won't deny I vibe coded this entire website, which is, I don't know, that's fine, who cares. So we got a little slider. How many coughs do you want to generate? Let's just say 8. There we go. Wow. Oh. Ah. Oh. Hey. Hmm. Hmm. It's a cute little website, but don't forget why we started doing this. There's just one more thing we need to do. I'm gonna fucking AI generate a bigger cough collection than this guy. 100,000. This guy collects coughs from small VTuber channels and other channels. He asks people to cough for him, and after that, he's gonna sell the coughs. And like generally coughs, like that's so fucking weird. And like what? He's done this for like quite a long time. Don't you have anything better to do? $100K coughs took about 50 minutes. We were averaging about like 35 to 40 coughs per second. Pretty good amount. Unfortunately, only about 20% of the coughs are, I'd call it decent. The rest are like a robotic mess. There's really a lot of stuff I can do to improve this, but I'm gonna leave it like this for now. So the question, can I teach an AI to cough? Yes. Can I completely automate can I literally make a cough factory? The answer is yes. What am I gonna do with all these coughs? Like, I don't know. What am I gonna do with all these coughs? Is it worth it? Is this entire project worth it to fucking make girl coughs? Is it? I don't know. You tell me.
さっきのところから帰れるね。うん。